Welcome back to bonding. In part 5 of this unit, we are going to be talking about molecular polarity, whether or not a molecule as a whole is polar, even though it might or might not have polar bonds. Okay, so first thing I want to go back and look at the notes page of definitions when we were talking about Lewis structures for covalent molecules. We said that these structures show atoms connected with 1, 2, or 3 lines to indicate the number of shared pairs of electrons. Polar covalent bonds should include partial charges, the partial positive, the partial negative, to indicate uneven electron sharing, but these symbols are frequently left off for the sake of brevity. Right now, we're going to include them so that we can see where the charges actually are in a polar molecule. The thing I want to talk about is polar bonds versus polar molecules, again from your definitions page of your notes. Even if the bond between two atoms in a molecule is very polar, the molecule as a whole may be nonpolar. If it is symmetrical, the direction of the charges cancel and the molecule is considered nonpolar. If there is an uneven distribution of positive and negative charges on the atom, the molecule is said to have a dipole moment, so oppositely charged at some point in time, and is considered to be polar. So if it's uneven or not symmetrical, it is a polar overall molecule, and we say that it has a dipole moment. Let's look at some examples. Okay, from your notes from your VSEPR page, we are going to talk about the polarity of each molecule individually, one at a time. So our first molecule on that page was HCl. Remember, we decided that it had a bond angle of 180 degrees, and remember we said it had no bonding pairs or lone pairs because there is no central atom, and that this molecule is linear. All of those things we'd already talked about for HCl. Now what we're going to talk about is whether or not the molecule as a whole is polar or nonpolar. Get rid of all this stuff. So, if we think of the guy over here on the left as the hydrogen, and the one on the right as the chlorine, just for argument's sake. Well, we know that chlorine is extremely electronegative, at least compared to hydrogen. So chlorine, this side of the molecule, is going to get the partially negative charge. Hydrogen is then going to get the partially positive charge, which means that there's a negative side to this molecule, and there's a positive side to this molecule. So since there's oppositely charged sides, there is polarity here. This molecule is polar, or we could say it has a dipole moment. Now if you look at this next linear molecule, the BeCl2, this one had 2 bonding pairs and no lone pairs. It was also linear. It also makes a line. It's just a different type of linear. So again, we're going to pretend like the guys on the outside are the chlorines, and the one in the middle is the beryllium, Be. Hold on, let me make that a good E. Yeah, beryllium. So chlorine is further to the right on the periodic table, so the chlorine is going to be the partially negative atom. And beryllium is further to the left, which means it's going to be partially positive. Beryllium has the lower electronegativity, chlorine has the higher electronegativity. So this time, the negative side of the molecule is all the way over here on the left, and also all the way over here on the right. So there's negative charges on both sides symmetrically, and then the positive charge is right here centered in the middle. So we can't say that over here this is the negative side and this is the positive side, because it's not true. There's totally symmetrical sides. So this molecule as a whole is non-polar, or it does not have a dipole moment. Let's look at the next one. We've got AlCl3. That one was trigonoplanar with bond angles of 180 degrees. We're going to pretend the Cl's are the outsides. I guess we're not pretending. We know the Cl's are the outsides, and the Al's in the middle. Since chlorine is more electronegative, the chlorines are partially negative, and the aluminum is partially positive because it's less electronegative. So again, do you notice that there is a line of symmetry through this molecule? If I draw a line right there, I've got total mirror image on both sides, completely symmetrical. I can even draw a line right here, and there's a line of symmetry. I can even draw a line right here, and there's a line of symmetry. There is no, this is the negative side is on the right, and the positive side is on the left. It's completely symmetrical. So this molecule is non-polar. But when we move to the one directly underneath that, the O3 we said was bent planar. It has 2 bonding pairs and 1 lone pair. Let's see, we're going to put an O, an O, an O. So it looks like, since they're all O's, they all are going to have the same charges, and so it's all going to be totally nonpolar. Except remember that this is a lone pair of electrons, a giant ball of negative charge. So if you were thinking about symmetry, you might say, hey, look, there's a line of symmetry. But really, there's not so much a line of symmetry there. Let's see if I can get rid of that line. I mean, although there is a line right there. What if we looked at it, let's make this negative right there. What if we looked at it this way? Then we see that on this side we have an oxygen, which is more electropositive, and a lone pair of electrons, which is much more electronegative, and there's obviously not symmetry going on there. Another way to think about it, let's see if I can erase all of this. Well, there's a lot to erase here. Another way to think about it is, this right here is a giant ball of negative charge, which makes the whole top of this molecule negative. And these are less electronegative than actual negative charges, so this side is the partially positive side of the molecule. We have the partially negative side and the partially positive side. There's obviously polarity here, opposite charges. This molecule is polar, it has a dipole moment. Next we've got the atoms that have 4 regions of electron density around the atom. So, or around the center, I suppose. So we're starting with CH4, which is tetrahedral, 4 bonding pairs, no lone pairs, and total and complete symmetry. There is not a negative side or a positive side. It's completely symmetrical no matter which way you draw it. There's total and complete symmetry here. This molecule is nonpolar. But when we move down to NH3, there's a lone pair, and that lone pair acts as the partially negative side of the molecule. So we have negative where the lone pair is, and positive where the hydrogens are. So there's 2 oppositely charged sides to this molecule, so this molecule does have a dipole moment. Same thing with the water, the bent non-planar. We've got a negative side up here where the lone pairs are, and a positive side down in the bottom where the hydrogens are. So this molecule is also polar. It kind of looks like, at this point, if you have lone pairs on the central atom, you are going to have something that's polar. But that's not always the case. Let's keep going. These are the 4 molecules that have 5 regions of electron density around the center. Starting with PCl5, there are no lone pairs. This guy is completely symmetrical. And this guy is totally non-polar. If you went in to add the partial charges, phosphorus in the center, chlorine on the outside, chlorine is partially negative. Phosphorus is partially positive. All of the chlorines are partially negative. But since all of the outside atoms are partially negative, all of their dipoles cancel, and so positive. And so this as an overall is nonpolar. So let's take out one of those atoms and change it into a lone pair. SF4 was a seesaw. Now we have this negative lone pair, which causes the whole top of that molecule where the lone pair is to be negative, and the whole bottom of that molecule where the atoms are to be positive. So this molecule is polar. Okay, so now we're going to take away 2 of the atoms from the original trigonal bipyramidal and make 2 of them lone pairs. So now we have big giant negative charge where those lone pairs are, and a relatively positive charge where the atoms are. BRF3, or T shape, is polar. And here's where it gets tricky. I3 has lone pairs. But what you should see about these lone pairs is that they themselves are symmetrical and centered on the molecule. We have partially positives with the atoms on the outside and partially negatives with the electrons in the middle, and all the partially positives and partially negatives cancel out. There is total symmetry here, even though it has lone pairs. This linear molecule is non-polar. Even though it has lone pairs, the lone pairs themselves are arranged symmetrically, and this linear molecule is non-polar. Let's move on to the molecules that have 6 regions of electron density, starting with the octahedral Sf6, totally and completely symmetrical. All the negative charges and positive charges cancel out. This molecule is non-polar. When we move on to BRF5, you see that electron at the bottom, the electron pair at the bottom, that causes the bottom to have a negative overall charge and the top to have a positive overall charge. This molecule is polar. But when we move to XeF4, we've got a lone pair at the top and a lone pair at the bottom. The lone pairs themselves are arranged symmetrically. Since the lone pairs themselves are arranged symmetrically around the rest of the atoms, which are also arranged symmetrically, this molecule does not have a dipole moment. It is non-polar. Okay, well, hopefully that helped explain which molecules can be polar and non-polar. Even though the bonds themselves are always polar in these molecules, the molecule as a whole might be non-polar. Join me again next time for hybridization.